Hi guys, Sarmad Bajwah here for our final video, the control modules video for Millie's flying fish. For this module, for this assessment, for this video, we have two tests that we need to do. And for test one, the system will move to a fixed angle straight on startup, hold this position for 2 seconds, and then move to a fixed angle of -10 degrees relative to the startup angle. I'll just quickly go through my code. Very basic, initializing the servo, telling it that we've attached the servo to pin 9, and then obviously we will move to 20 degrees on startup, wait 2 seconds, then move to 30 degrees, which is -10 degrees, and then wait for 10 seconds. The reason I'm saying that it's -10 is because 20 degrees for us is actually 180 degrees on our protractor, and then -10 degrees to that is 170. But since the servo motor isn't calibrated properly, we've had to make some adjustments, so therefore it says 30 degrees. So I'm just going to start the system now. It should move to 20 degrees, wait for 2 seconds, then move -10 to our 30 degrees. Alright, now we're going to do test 2. For test 2, we have to move the fin to a fixed angle of 15 degrees on startup. Then we have to slightly move the fish on the fulcrum, slightly rotate the body, and our control system should be able to keep that same angle of 15 degrees. So that's what we're going to do. But before I show you the demonstration, I just want to quickly mention that we've got a few control dynamics that we should talk about, such as overshoot and undershoot, and they relate to our PID gain adjustments, namely KP, KI, and KD. KP is our proportional gain, so basically it responds directly to the error that we're getting. Increasing it makes the system more aggressive towards the errors, decreasing it makes us have a slower response, and that reduces overshoot, but it takes longer to reach the target. KI is our integral gain, so basically what it does is it accumulates error over time and corrects it for a steady state offset, so increasing it will eliminate persistent small errors faster, but it causes instability. Decreasing it reduces the risk of oscillation, but may leave us with a small error. KD is our derivative gain, so it responds to the rate of change of error, providing damping, making it smoother. So increasing it reduces the overshoot by predicting any future errors, but it can amplify any noise. Decreasing it makes the system have less damping and probably results in more overshoot, but it makes the system a lot more smoother. So just gonna quickly show you guys my code that I've got here. So obviously we introduce all the libraries. We've got our KP, KI, KD values, so I've done a bit of fine-tuning to find these values. And then we've got our limits and smoothing values. And then the rest of the code that just measures the tilt, basically all of the PID stuff, and that's all there. So it's already hooked up, but I'm just gonna take it off and then hook it back on, and we'll see that it's going to do some, I guess, setting up calibration sort of stuff. Okay, and yeah, now we're at our 15 degrees, and you can see it's stabilizing. Okay, and now if I move this way, the fish's body this way, we can see it tries to maintain that 15 degrees. And if I move the other way, it's also working to maintain that same angle of 15 degrees. And we can see if we go perpendicular to the servo motor, the fin is still at 15 degrees perpendicular to the servo motor. If we go back here, we're still at our 15 degrees. And we go this way again, and it's still working to maintain that angle of 15 degrees. So yeah, we can see that the PID control is working. And yeah, if we bring it back to the center and leave it for a bit, it should stop moving, because now it's got that angle that it wants to achieve. And then yeah, the second we start moving it again, the PID control system kicks in. So thank you for watching.